Hi everybody, here's your video on an introduction to differential equations and slope fields. These are two of the last topics that we're going to be doing right before L'Hopital's rule. So we're getting close to the end here. Now the thing with slope fields is these are a relatively new topic to the AP exam. They started in 2007 as multiple choice. A few years ago they started appearing on free response questions. So we'll be practicing a lot of them because they have been a recent trend here. To introduce differential equations and slope fields, let's do a quick warm-up here to remind yourself of how we're going to use this here. Let's say I give you a derivative, and let's say the derivative is 2x. And then I also give you an initial condition, and that initial condition says that f of negative 1 is 3. I want you to find f of x. So pause the video for a minute and solve for f of x here. Don't forget your plus c that you have to find. Hopefully what you got is when you do the integral, you get x squared plus c. Using your initial condition, I plug in my x and my y, I get my c value, and then I can replace it here. And this is my actual function f of x. Now the reason I had to do that is we're going to use this fact once we start drawing slope fields. So let's talk about differential equations here first in general, and then we'll do slope fields. So whenever we're going to learn this topic, we'll do slope fields first, and then we'll solve differential equations second. So in general, differential equations talk about how things are changing, specifically without talking about an explicit function y. So a differential equation is always going to have dy dx equals something. And it's not going to say what y equals, it's what the derivative equals. And your goal is going to be to find the function y whose derivative, which is going to be the dy dx here, appears in the equation. You have to keep in mind what the goal is. And that's always going to be to find the function y. You are done whenever you have y equals blank. So it's going to be similar to what we did here where we found what y was equal to, but the notation's a little bit different and it's going to be a little more complicated. Examples of differential equations look like this or like this. Just keep in mind dy dx is slope. So what you could say instead is that I have a function whose slope everywhere is equal to x to the fourth. You can have a slope that's only in terms of x, or you could have a slope that's in terms of x and y. So what this is saying is that the rate of change of y with respect to x, that's basically what dy dx means, is calculated by doing x plus y at any ordered pair. And that's what we're going to be doing very soon when we graph slope fields. So pause the video and make sure you're copying down as you go here. Now keep in mind, we know how to do antiderivatives, but the thing is, I've been giving you a lot of integrals that you can do without a problem, but the thing is there's lots of antiderivatives you actually can't take. For example, this. No one knows what the antiderivative of that is, and in fact there's more antiderivatives that you can't do than antiderivatives that you can do. It's just I've been giving you ones that you can do. So the solution is, let's say you have a dy dx, and you really want to find what y is. You'd have to do an integral, but again, let's say you can't find the antiderivative because it's too complicated or it just doesn't exist. What we can do is use slope fields. Now, another thing quick is, for things like this is really easy. Like if you know that the derivative is x to the fourth, then you know that y would be x to the fifth over 5. You can do that antiderivative easily. But with something like this, like we don't know how to do the antiderivative. And in fact, in this class, you're not going to learn how to. It's too complicated. So slope fields are going to come to the rescue here. And this method is going to help us more than integration will. So what happens with slope fields is you use your derivative or your dy dx statement, which is one of these two things. And what you use them for is to visualize what the function looks like. There should be an L right here. There we go. So it's going to be to visualize what the function looks like for all the infinitely many solutions. And I'll explain what this whole infinitely many solutions means in a moment. So what we're going to be doing is we're going to be getting slopes at a subset of the plane. Now that just means so you don't have to do this forever over the whole plane. Usually we'll be doing -3, less than or equal to x or y, less than or equal to 3. And what you'll be drawing is tiny, tiny, accurately tilted line segments. And what these line segments are little baby tangent lines. So you'll be drawing a ton of little tangent lines to help us see what y looks like. Because remember, that's the goal here, to find a function y, and if you can't, then at least to visualize y. And the reason we can use a line to visualize what a curvy function would look like is because of local linearity, which says that if you zoom in a lot on a curvy part of a function, and if it's differentiable, then it's going to appear straight. That's what local linearity was. Don't forget that. And again, slope fields are a way to graphically get... What the heck? Hold on. Anyway, it's a way to graphically get and visualize solutions to differential equations. So what you have in your notes is this taped down on page 1. So hopefully these notes you put around it, and we're going to put a few things on here. So let's go to this picture right here, and I want you to take a moment and just think about what you're actually looking at. And hopefully you realize that this is a family of functions, x squared plus n, some constant. The reason it's plus n is because sometimes it's x squared plus 4, or just regular old x squared minus 4, x squared minus 8, etc. And the way that we have transformed these is we've shifted them up and down, so it's a rigid transformation. It's not like you're stretching or shrinking it. What I want you to do is pause the video. Now this is important that you actually do this here. Pause the video, and I want you to draw little tangent lines on the graph for x being -1, 0, 1, and 2. Now remember, to draw a tangent line, you have to find the slope. So get the slope of this. That should be a real quick slope to find, a derivative. And so I'll do one with you. So let's say at x equals -1, the slope is 2x. So that's what dy dx is. And then -1, that'd be 2 times -1, which is -2. Where's my thing? So you're going to go here and draw a little baby tangent line, whoop, right there with a slope of like -2. So do that on all the curves at all these x values, and then come back. What you should be looking at is something like this. Now notice we started with a bunch of functions like this, a family of curves. When you draw your tangent lines, you get this. Notice that at the x value of 1, for example, they all have the same slope. At the x value of 2, they all have the same slope. And let's say I were to take this picture and remove the actual function curves and only keep the little baby tangent lines. Then you would get something like this. And this is a slope field right here, your very first slope field that you're looking at. A slope field suggests right here a family of solution curves. Now what you want to think when you look at a slope field is, remember, these are baby tangent lines. You find the derivative at a bunch of points, you draw accurately tilted baby tangent lines that have the slope of whatever the derivative value was. And when you look at a slope field, you want to think, what if I dropped a pebble in this river here and it were to follow the flow of the stream? Where would it go? Just remember, follow the flow here. So you can see they're tilting down, they flatten out, they tilt up. So slope fields help you visualize what a function looks like based off of derivative values. So again, it gives us an idea about the shape of a function y. And again, when you look at a slope field, an important thing to realize is you have infinitely many solutions. A slope field only tells you, a slope field tells you the general shape, but there are infinitely many parabolas that could be fitting in here. The only way you get one unique solution is if you have an initial condition. So this is just like the warm-up where I said, okay, the derivative was 2x, which the derivative was 2x everywhere. And on the function, I have f of -1 equals -3. So in that case, if you were given an initial condition right here, then you would know, oh, okay, I have to drop my pebble here so that whenever it follows the flow of the river, it's this specific curve and not any of the others. So this is how a slope field works. A unique solution is given only when you have an initial condition. So let's practice drawing some. So now what I need you to do is go to that half sheet of paper that had a bunch of slope field grids on them. I've zoomed into one of the slope field grids here. For the first example, right above it in this space here, you can label it as dy dx equals 3x squared. For this example, I want us to draw a slope field from -3 to 3 for x and y. That just means I'm going to be in this box right here. So that way you're not drawing little tangent lines forever here. So what you're going to do is you're always going to use this, whatever dy dx equals, for your calculations. You're going to plug each ordered pair into here. Now notice, if you're to plug an ordered pair x, y into here, y isn't going to matter. So for this slope field, you want to look for patterns like this when you do this. For this slope field, y doesn't matter, only x is going to affect the slope's value. So I'll do a couple with you and then I'll have you finish it off. Let's take the ordered pair 1, 1. You can start wherever you want, really. If I were to plug 1, 1 into here, again, I can only plug the x part in. That'd be 3 times 1 squared, which is 3. So go to 1, 1 and draw your best effort here at drawing a slope of 3. Now, I know it's going to be hard, especially when the slopes are close, but I'm going to start here and say, all right, if the slope were up 3 over 1, it would be that steep. So just draw one little tangent line that steep. Let's do 2, 1. Okay, so I'm going to take my ordered pair, only x matters, plug it into here. 2 squared is 4, 4 times 3 is 12. So a slope of 12 is pretty steep here. Go to 2, 1, and if a slope was 12, that'd be really steep. Now let's say 3, 1. If I plug 3 into here, 3 squared is 9, 9 times 3 is 27. That's like almost a vertical line here. I'm going to do one more with you. How about 0, 1? If I plug my x into here, 0 squared is 0 times 3 is 0. So I have a flat curve right there. So you keep going and do all the ordered pairs from -3 to 3. Only the integer values, obviously. That's what these dots are for. And then come back. Hopefully your slope field came out looking something like this. All of these lines here and here had a slope of 3. All of these guys had a slope of 12. And these all had a slope of 27. And right here, they all had a slope of 0. Now, the AP exam knows that you're not computers, so you can't draw these perfectly. All they care about is the slopes relative to one another. So obviously, a slope of 0 should be flat. And they will just care that this is steeper than this, and this is steeper than this. So as long as they're getting steeper and steeper. Now, let's try and imagine what some solution curves would look like. First of all, did we even need a slope field to visualize a solution? Let's think, do I know what the antiderivative of this is? Yes, we do. That would just be x cubed. And if you look at this, hopefully you can picture like a pebble starting around here, following the flow, starts steep, gets a little less and less steep, flattens off, starts not that steep, gets more and more steep. You have infinitely many solution curves here. They're all cubics. Now, we know it's cubic here, but you won't always know. And let's say I gave you an initial condition, and I said, all right, I have a specific solution curve that goes through 1, 2. Then you could anchor it down here, and you could draw yourself the unique solution curve. Now, when you draw the unique solution curve, you want to go all the way from the left to the right here. Let's do one more. For example 2, let's do this one here, dy dx equals x plus y. This is what I'm using for my calculations. Notice x and y both are going to affect my slope here. It's in terms of both of them. So again, you're going to go from -3 to 3. So I'll do a couple points with you here. And sometimes the pattern jumps out right away. Sometimes it takes a while here. So if I was at 1, 1, then my slope would be 1 plus 1, which is 2. So I'm going to picture, okay, a slope of 2 will go up 2 over 1 like that. Let's do 2, 1. 2 plus 1 is 3. So right here the slope's a little bit steeper. Let's say, oh, that's way too steep. That slope is 3. Let's do 3, 1. That slope would be 3 plus 1, which is 4, even steeper, like that. What about 0, 0? 0 plus 0 is 0. So I want you to go around. Let's do one more. 0, 1. 0 plus 1 would be 1. That slope would be not that steep. 1. Go around and do all the ordered pairs, and then come back and check how you did. This is what your slope field should resemble. Now this one, the patterns took a little bit longer for me to see when I first did this, but you should have realized that all of these points here have a slope of -1, and this is actually going to be a slant asymptote here, which is dividing our plane into 2 different types of solution curves. Your curves cannot go through the asymptote, so it's going to divide it. Hopefully you also notice that all of these points where the x and y were the same but opposite has slopes of 0. So if I were going to sketch solution curves, some of them will look like that, and some of them will look something like this. All right. Now in class, next time I see you, we'll mess around with the slope field program. Until then, I want you to do these 4 extra problems on your sheet, so they'll fill up all the grids. Do all of them from -3 to 3 except this guy. Extend your y's from -6 to 6 so you see it better. And I'll see you on Monday.